Welcome, ladies and gentlemen, to our second lecture on sound and our last lecture on mechanical waves. Today we're going to look at a few more properties of sound waves, but we're going to do it specifically through the lens of music. So let's start our discussion of music by discussing standing waves. Remember that when we had a string fixed on both ends of some length L, then the string would vibrate with what we called normal modes, right? And the first normal mode was just the vibration of the whole string like this, right? And these normal modes are waves, standing waves on the string with wavelength lambda n equals 2L over n. And then n was any integer, right? 1, 2, 3, etc. Okay, out to infinity. Now, when we consider this string, let me draw one more. So that was n equals 1, right? Where the wavelength is twice the length of the string because this is half of a wave, right? So then n equals 2, you can see if I make n equal 2, then the wavelength is the length of the string. That means I have a node in the middle, and I have a full wave on the string, right? And then because this thing is vibrating up and down, we get this. And remember, we have the node where the string doesn't move, and then we have the antinode where the string moves maximally, okay? And for each normal mode, as we go up, we keep adding another node, and we keep increasing the wavelength, okay? So, we keep decreasing the wavelength. We keep increasing the nodes and decreasing the wavelength. But it always has to be such that a number of half wavelengths add up to the length of the string. Okay? So now, consider that if we make this string vibrate with a specific frequency, right, one of the normal modes, it has to move air to vibrate, right? As it goes up, it has to push these air molecules out of the way, right? And then they're going to compress, and they're going to have areas of lighter pressure, and they're going to have areas of more pressure. Okay? So I'm going to create this wave going out of pressure. And a pressure wave is sound, right? And it's going to have, that sound is going to have the frequency of whatever the string has, right? Because the string is physically pushing the air around. And the fact that this string that's fixed, remember it's fixed here and it's fixed here, the fact that it's fixed and so it produces these normal modes means that the vibration occurs at very predictable frequencies, right? Specifically that first normal mode, that what we called the fundamental frequency, right? And that was the normal mode for n equals 1, where the wavelength is just half, right? The length of the string is half a wavelength, and so the whole string vibrates like this. So specifically, it's going to produce that note most strongly, right? And this is indeed the exact way that we use something like a guitar, okay, or a piano. If we want to make a really low note, we might have a really long string, right? And then the guitar is a really nice example because what we do is we pluck this string and it vibrates and we make this note, right? But if we want to make the string play a higher note, what do? We take our finger and we press on it, right? And we pin it against the neck of the guitar. Well, what does that do? Well, that means we shorten the length of the string, right? We create a node here, and the node back here is still there. And so now when we pluck it, the fundamental frequency is this vibration, right? And L is shorter, so the wavelength is shorter, which means the frequency is higher, okay? And so we get a higher pitched note. Now we do the same thing with the piano, only the strings have different lengths like this, okay, to create the different notes. And of course, we do the same thing with any other stringed instrument, a violin or a ukulele or something like that. We pin the string against the neck to make the string shorter, okay, and change the note that it makes. And this ability to produce predictable frequencies, this is what allows us to make music, right? To be able to play the same thing over and over again, okay? But not all instruments are string instruments, right? Guitars and violins and ukuleles and things like that, those aren't the only instruments we have. Some instruments, we make sound by blowing air into them, okay? And what happens is very similar to our string, okay? So with something like a flute or a trombone or a clarinet or something like that, or even your voice, we blow air through a pipe, okay? And what we do is we have this column of air, and we create a standing wave inside, okay? We create a standing pressure wave. Well, the pressure wave moves. We create a standing wave of displacement of the particles, okay? And so when we create a standing wave in a tube, we have particle displacement nodes and antinodes, okay? So we have spots where the particles don't move, and we have spots where the particles move maximally, okay? And you can see just from my picture, if I draw this, if this particle moves maximally and a particle right here doesn't move, then their distance between each other changes a lot, right? So what I end up with is that this thing becomes a pressure antinode, okay? And over here, where we have this kind of maximum displacement, we end up with a pressure node. And that one's a little harder to visualize, but it's because of the fact that all the particles in here are oscillating. And how much they oscillate depends on position, okay? And so what we end up with is right around in here, the particles are always about the same distance apart, okay? So we end up with a pressure node. And over here, where we have a displacement node, we have a pressure antinode, okay? So we always get a pressure node at a displacement antinode, and we always get a pressure antinode at a displacement node, okay? So that's all great. We can create standing waves in a tube of air. But what about boundary conditions? Remember that when we create these standing waves, they're very much dependent on the boundary conditions. In fact, to be defined, they require boundary conditions. Remember with our string, we had the boundary condition where, remember when we were shaking one end, we had two kind of boundary conditions that we could have here. One was fixed, right? Where the wave would get to this, and remember it would turn over and come back. And one was allowing it to move up and down. Okay, and remember that sent that if I sent this wave in, what comes back is the same, right? So those two kinds of boundary conditions, they have analogous boundary conditions in a column of air. So remember when I fixed the string at both ends, I created nodes here, right? This was a node by definition because I didn't allow it to move, and that's what nodes do. They don't move, right? Similarly, if I take a pipe and I close one end, I create a displacement node here, right? Because if there's a little particle right here, when other particles bump into it and stuff, it can't move, right? The wall of the pipe is in the way. So I force there to be a node at this position, okay, with the closed end. On an open end, I have the exact opposite, okay? On the open end, I have a constant pressure pushing it on it, pressure of the atmosphere. And so I create a pressure node, right, which is a displacement antinode. And so if I draw this using displacement terms, I have a node into an antinode. Okay, now what I'm drawing here is a sine wave. Okay, so you can imagine if I draw up here real tiny, I'm drawing from the node here a sine wave that goes like this. Okay, and then on the other side, I'm just drawing the other corresponding sine wave that goes like this. Okay? And so if I look at just one of these things, this would be a wavelength, right? It's crest to crest of this one. That's a wavelength, right? So from the node to the antinode on my closed pipe, this is 1/4 of a wavelength, okay? You can see I would have 1, 2, 3, and 4/4 to be at the same position, going the same direction, going up like this, okay? So this is 1/4 of a wavelength. So my closed pipe here, with this 1/4 of a wavelength, that's the fundamental frequency of that, right? So lambda n is always going to equal 4L over n for this closed pipe, okay? It's going to equal some number of quarter wavelengths. And then n equals 1, 2, 3, etc. Okay? Just like for the string. Only now we can have one end open. When we had one end open on the string, that didn't work, right? Because then that open end just flails around. But with the pipe, we can have one end open, okay? And it creates this quarter wavelength. But then what if we change it? So this is one end closed, okay? But then let's redraw this. With both ends open. So what happens then? Well, now I have to have an antinode on one side and an antinode on the other side, okay? And to do that, I have to have something like this, okay? And that means that now, see, I'm going from crest to trough on this one wave, right? Crest to trough. Oh, let me put this on the bottom to give us some space. So crest to trough is 1/2 of a wavelength, right? Because crest to crest would be a full wavelength, and this is 1/2 of that distance. We're just going crest to trough. So then lambda n equals 2L over n. N equals 1, 2, 3, etc. for an open pipe. Okay? And this one end closed, we're going to call that a closed pipe. Okay? Now, theoretically, one of our pipe could have 2 closed ends, right? But then there's not a way for the sound to get out. And when we blow air into it, we just increase the pressure in the pipe. Okay? So the 2 closed end situation doesn't allow us to create standing waves, okay? But we can have a closed pipe, which is one end closed on the pipe, and we can have an open pipe, which is both ends open, okay? And these different wavelengths, these give us the normal modes for these 2 different pipes, right? So then, if these wavelengths give us the normal modes, then for the normal frequencies, right, Fn equals Nv over, and then the number, either 4 or 2, so 4L for the pipe, right? Because remember that V equals lambda F, right? And the V is a property of the medium. So in this case, air, because we're talking about blowing air through these pipes, right? And so then F equals V over lambda, right? So we have V on the top, and then we have lambda flipped upside down, okay? And then, of course, the fundamental frequency is N equals 1, right? So this is, again, for the closed pipe, because we have the 4, right? And then the Fn for the open pipe, again, is V over lambda. So this is open. And then you'll notice if I make n equal 1, I get F1 is the fundamental frequency. I don't have space. Let's make some space here. Let's get rid of this picture. This picture's not doing us any good. Okay, so F1 is the fundamental frequency, okay? And of course, that's just going to be V over 4L for the closed pipe, V over 2L for the open pipe, right? And then all the other frequencies for the normal modes are going to be Fn equals N times F1, right? And again, N equals 1, 2, 3, etc. Okay, so those are going to be the frequencies of all the normal modes. The normal mode is defined by the wavelength, right? It was the length of the pipe and then the length of the wavelength of a standing wave that we create in that creates the normal modes, right? That's what decides where the nodes and the antinodes are. That's what creates the normal modes. But then what we hear is the frequency, okay? And you can see that we had to use the velocity to get the frequency, the velocity of the sound in the medium, right? In air. So if we change the velocity of sound, then we'll change the frequency, right? The normal modes won't change because that was based on the geometry of the pipe, right? And then the actual wavelength of the wave that'll fit in there. And the wavelength doesn't change. So if I change V, if I do something like, say, inhale some helium, right? Then the speed of sound in helium is different than the speed of sound in air, okay? And what happens? It changes the pitch of my voice, right? If anybody's ever heard someone who inhaled some helium speak, your voice gets really high, okay? And that's because we change the speed of sound because we make it move through helium instead of moving through air, okay? So we changed the frequency. But it didn't change the geometry of our vocal cords, okay? Our vocal cords are still shaped the same. And that means that these wavelengths didn't change, okay? The normal modes stayed the same because the normal modes are based on wavelength. And when we change the velocity, we just change the frequency that those wavelengths elicit, okay? So we have a few of these different methods for creating a predictable frequency here. We have the vibrating string, right? That physically moves air, and then we get a pressure wave moving through the air, okay? That's our guitar, our ukulele, our violin, our cello, things like that, okay? We have an open pipe, all right? And something like a flute is an open pipe, okay? It's got an opening on both ends. And then we have a closed pipe. And usually for an example for that, we use a clarinet because it's very pipe-shaped. Something like a saxophone is more of like a closed cone instead of a closed pipe. But something like a clarinet, we consider it closed because the end that you blow in, the end with the reed, is pretty well stopped, and the hole is so much smaller than the bore of the tube that it effectively acts as a closed end, okay? And your voice is actually approximated. It can usually be approximated as coming from a closed pipe because at one end of your vocal cords, the hole that air goes through is much, much smaller than the diameter of the vocal cords, okay? So your voice is usually, when I've seen it modeled, it's usually modeled as a closed pipe, okay? But the important part is that for each of these instruments, when we create a particular frequency, we'll still have different overtones created, okay? Different additional normal modes that are established based on the instrument, right? So we can have two instruments play the exact same frequency, which means they play the same note, okay? And we can still have two instruments sound very different while playing the same note, okay? A good example of this is you could have a flute play, say, a middle C, okay? And that's a note with a specific frequency. And we'll get to that in a second. And you can have a piano play that same note. Now, the pitch of that note will be the same, but the two instruments sound very, very different, right? And that's because they create a whole bunch of different overtones. The way that they create that note is a little different. The normal modes on the string of the piano and the normal modes in the pipe of the flute are different. And so the overtones, those extra frequencies that are vibrating on there, in addition to that fundamental frequency, those are different and they make the instrument sound different. Okay? We know that sound comes from pressure waves, and those pressure waves have a certain frequency. So we know that any difference that we hear in sound has to come from adding different frequencies, right? And there's a lot of things that can go into that, to adding frequencies to the main frequency that you're playing, right? The musical note is the main frequency, maybe the strongest, the highest amplitude frequency, but all these other frequencies have to be in there for it to sound different, because all that matters for sound for us is frequency, right? And so we change the wavelengths and the frequencies that are normal modes by changing the conditions of the instrument to modify the boundary conditions, right? This was our example of the guitar, where we pin the string against the neck to change the length of the string. And we change the boundary conditions, right, by putting a node in that spot. And we set up a new set of normal modes, okay? So we build these instruments that can produce predictable frequencies for us, and they always end up vibrating the air at that frequency, producing a predictable pitch, right? So if I have a guitar and I have it tuned, if I just pluck that top string, every time I pluck it, I get the same exact sound, right? I get the same pitch. So then what we do is we define specific pitches, specific frequencies, and we name them so that we can compose music, right? The whole point of writing music down is so that I can give it to someone else and they can play the thing that I had in my head, right? I communicate how to play the song that I thought of, and then somebody else can play it because I've defined notes, specific frequencies, and then I was able to represent them with either talking to the person or writing it down or whatever, right? Or even just playing it for them. But then they have to be able to play the same frequency. So the fact that the musical instruments produce predictable frequencies, that's key to this whole thing, right? I have to know that every time I pluck that string on the guitar, it's going to play the same note, okay? So then we put all this together and we can create pieces of music. And in normal musical composition, the notes that we have are A, B, C, D, E, F, and G. Okay? And these notes are cyclical. So usually, actually, we consider one octave to kind of start with C. So we might have like C4, and then we'd have D4, right? E4, F4, G4, and then A4 and B4. And then the next C comes around, and that would be C5. Okay? And so they work like this. We have C, and then of course we have D again, and E, and etc. They're cyclical like that. So in that case, they're kind of like a sine function, but they don't vary in amplitude in the same way that a sine function does, right? But they are cyclical in the way that a sine function is cyclical. So I've listed a few notes here just for reference, and I have some frequencies for them, okay? And you can see the note here, and we have the frequencies here. And then we have what are defined as half steps. So C, there's a half step in between here. There's a half step between D and E, okay? And this half step is either what's called C sharp or D flat, okay? This C with the number sign above it, that's a sharp, C sharp. And this D with a little B above it, that's a D flat. And C sharp and D flat are the same note, okay? They're the half step between C and D, okay? There's another half step between D and E. E and F actually is a half step. There's no half step between those. And then between F and G, there's a half step. Between G and A, there's a half step. And between A and B, there's a half step, okay? And then between B and C, that is a half step. There's no half step between B and C, okay? It's a little bit confusing, but you can see the way I've drawn it. I have C, D, E, F, G, A, B, and C. And then my half steps are a half step here, right? A half step here. No half step between these two. A half step between F and G. Half step between G and A. Half step between A and B. Okay? And what does that look like? That looks like a piano keyboard, right? And indeed, that's exactly why a piano keyboard looks the way it does. The black keys are the half steps between the named notes, and the missing black keys are because these steps between these notes are technically half steps, okay? And the half step thing, it doesn't really matter. We can just consider all of the half steps to be a step, because when we define notes, what we care about is half steps, okay? I don't know why the notation is this way, why they didn't just make more musical notes, why they did the half steps. I have no idea, actually. But when we define frequencies for the notes, what we care about is these half steps, okay? So you can see, to go from C to C, I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and then 12. So if I go up 12 steps, I'm at the same note. Okay, so I went from C to C. And that 12 half steps up, that's an octave, okay? And these numbers on these notes up here, those dictate octaves. Now, C4 is called middle C. It's because it's in the middle of the piano keyboard. There's no other meaning. There's no like further meaning to that. It's just the C that's in the middle of the piano keyboard, okay? So this middle C, if I go up an octave to C5, you'll see that this frequency, it doubles, okay? And the same thing here, if I look at A4 and A3, the frequency an octave away, it doubles, okay? So what we do to define musical notes, to define their frequencies, is we pick one note and we pick a frequency for that note, okay? And a really common choice is this A4 right here. We pick it to be 440 hertz. Okay, and we just say that. We just say A4 is going to be 440 hertz. This is a really common choice, and then a lot of common choices are to change that 440 very slightly, to change it to like 438 or something like that. Okay, but still for this A4. But this one, the 440, that's very common. Okay, and so then a note is defined by the number of half steps away. Okay, so we showed our little half steps, and for a note, the frequency of that note is going to be F naught, okay? And in this case, F naught for us was A4 equals 440 hertz. So F naught equals 440 hertz, okay? And then we multiply it by this number A to the n power, okay? And A is 2 to the 1/12 power, okay? Let me rewrite that. And so we have 2 to the 1/12 to the n, okay? So I'll even rewrite it over here. So it's F naught times 2 to the 1/12 power to the n. And so now remember, when I counted out half steps, it was 12 steps to be at the same note again, right? So from C4 to C5 is 12 steps. So then N is 12. And what's 1/12 raised to the 12th power? Or 2 to the 1/12 raised to the 12th power? Well, it's 2. Right? When we have a power raised to another power, we multiply the powers together. And so we get F equals F naught times 2. And this F naught can be any note that we pick. So If we pick F naught to be this C4, then we'd go 12 steps up. That's 2 to the 12, 2 to the 12th, 1/12th power, to the 12th power. Then we get times 2, and so we just get F naught times 2 brings us this note here, 12 steps away, okay? But it works for all the notes. It's not just for the octave, right? This is the formula that we used to get all of these notes, okay? All of these guys. And all of the notes on the scale, okay? So if we wanted to add notes on the low end of the scale, we would just keep going down by these steps of 2 to the 12th, okay, to the N. And in this case, you have to pick one note out of the blue, right? I have to pick one so that I have an F naught to start with. Now, when I go from one note to another, I can make any note the F naught from there on out. But to just create the scale from scratch, I have to pick one note to start with. And this one right here is the note that's usually picked, okay? And I have no idea why. I think it probably comes from early on when they first started making musical instruments. They didn't have such a sophisticated way to pick these notes. They just kind of made the notes they made. And it probably turned out that, I'm guessing pianos. I'm guessing this is based from pianos. It probably turned out that the A4 on a piano had a really nice round frequency, okay? Because these, I've rounded them all to 3 digits, but they're all actually like 262 point something, right? I have it written down here. This frequency of this middle C is actually 261.626 hertz, okay? And I've rounded it to 262. But this A4 actually makes 440 hertz. The frequency is 440 hertz exactly, and I suspect it just happened to be the case that pianos, that A4 made it something that was a nice round frequency number. And so now when we make these scales, these musical scales, we start with that one because it's a nice round number, okay? And then we say, okay, it's exactly 440 hertz, and then we figure out what all the rest are, okay? But we use this formula here. And then to figure out what a note would be based on one of the notes, as long as I know any note, I can use any note in F naught. So if I wanted to know what an F2 was, and I wasn't sure what A4 was, but I knew F3 was 175 hertz, I could plug that into F naught and then count the half steps from F3 to F2. Okay, so 12. So it's going to be half the 175. Okay? And the other thing about this is the steps are positive or negative, okay? So if I wanted to get F4, then I would have F equals, and then let's put F3 as our F naught, times 2 to the 1/12th. And then if I wanted F4, it would be to the 12th power, right? And that would give me twice the frequency. If I wanted to the F2, it would be to the minus 12th power, okay? This N is negative when we go down. And then this 2 becomes a 2 to the minus 1, which is a 1/2, right? A minus 1 just puts it on the bottom of a fraction. So we end up with a 1/2. So the F2 is half the frequency of the F3, okay? So if we go up, we do a positive N. If we go down, we do a negative N, okay? And then this note to note, this 12 steps or 12 half steps, that's what we call an octave, okay? So when you hear somebody talk about maybe a singer can sing in, say, sometimes they say they have like a 5 octave range or something like that. 5 is extremely high, right? That's like Christina Aguilera or something like that. But say they had like a 5 octave range, that would mean that they can cover notes from 5 octaves apart. So like a C0 all the way up to a C5, okay? So 60 half steps. They can cover all of those 60 half steps, okay? So we define these very particular frequencies for particular musical notes. But what happens if we have two things that are supposed to be playing the same note, but they're off by just a little bit, okay? Now, of course, if they're off by a lot, somebody's just playing a wrong note, right? So if we go back for a second to our musical notes, if we both thought we were playing an A4 but mine was at 350 hertz, I would just be playing an F4. I would just be playing the wrong note, right? But what if we both think we're playing an A4 and you're playing it at 440 hertz and I'm playing it at 438 hertz or 437 hertz? So if they're only off by a little bit, by just a couple hertz, we get something called beats, okay? This isn't the kind of beats that the drummer's laying down. This is a whole different phenomenon, okay? So we have these two different wave sources coming together, and this time I just took a picture out of your book, okay? We're not going to rely on my drawing ability for this because we all know my drawing ability sucks, okay? So we're going to use this picture that I just copied right out of your book, okay? I just took a screenshot right out of your book for this thing. So we add our two waves with superposition. That's what's going on up here, right? We have these two waves, and you can see they're slightly different frequencies. And so they're starting kind of out of phase here, and then they get closer and closer to in phase. And then here, they're in phase with each other, right? But they're slightly different frequencies. So they're in phase for a moment, but then as we go this way, they start to get out of phase again, right? And then here, they're 180 degrees out of phase, okay? They're totally out of phase again. And then from being totally out of phase, as we go this way, they work back to in phase, right? And this happens because they have slightly different frequencies, all right? So as we hold each note, they'll have moments where they're right in phase and right out of phase, and this is going to shift. And what we end up with, if we just add these two sine waves that are on the top, we get this thing on the bottom, okay? So what do we get? Well, we get this frequency it's not quite either one of those frequencies, but it's pretty close. And then we get this periodic change in volume, okay? So you can see we have a big amplitude here, we have a little amplitude here, and a big amplitude here, okay? And this volume kind of pulses. And that sensation of the pulsing volume is usually something you can hear as kind of a waver when two things are just a little bit off, okay? And we call the frequency of this waver the beat frequency. So listening for a beat frequency in a sound is a low-tech way to tune a piano or something like that, okay? So if you want to tune a piano, you can take a tuning fork, right, for a particular frequency, and you can strike the string on the piano, and you strike the tuning fork, and you hold them so that you can listen to both kind of equally at the same time. And when they're close to each other, when they're close to the same frequency, you'll hear this kind of waver, okay? You'll hear this volume kind of going up and down. When they're the exact same frequency, so you change the tension on the piano string a little bit. When they're the exact same frequency, then this beat goes away. Okay, and what you'll hear is, remember, if they were both in phase, I would hear this. They would be in phase like this, and I would hear just an increased amplitude, right? And so the piano string then is in tune. It's like perfectly in tune when this beat frequency goes away. Okay, when you can't hear it. Now, if it's really out of tune, you'll probably be able to hear that they're different frequencies, but you won't really be able to hear a beat frequency because it'll be too fast for you to hear it, okay? But then as they get really close, once they're only a couple hertz apart, well, you can hear something changing on a time frame of a couple hertz, right? So this one that's shown here, this is a 2 hertz, okay? Because it goes through the cycle twice in 1 second. So this is a 2 hertz beat frequency, and you could definitely hear that, right? You could probably even hear 3 or 4. You might even maybe be able to hear 5 or 6, but above that, you're probably not going to be able to hear the beat frequency anymore. Okay. And so this beat frequency comes from two sound waves being just a little bit different. Okay, just a few hertz different, and the frequency of the beat is equal to F1 minus F2. And frequencies, of course, are always positive, right? We don't have negative frequencies, which means that F2, we always have to make that the lower frequency. Okay? So if you have two frequencies, whichever one's lower, that becomes F2 in this equation, and then we can calculate the beat frequency just by taking the difference between the two, okay? Now the problem is, if I just hear the beat frequency, I don't have any idea what the frequencies are, okay? It only tells me the difference between the two frequencies. So the beat frequency between, say, 130 hertz and 132 hertz would look exactly like this picture, okay? But the beat frequency between 2300 hertz and 2302 hertz would look exactly like this picture, okay? They would look exactly the same. Well, I guess not exactly, because these things would be a different frequency, right? But the beat frequency, you'd still end up with a 2 hertz beat frequency. So the beat frequency itself isn't going to tell you what the absolute frequency is, what the two frequencies are, but it will tell you the difference between the two. And then the frequency of sound that you're listening to, the frequency of sound that you're hearing the beat frequency in, that of course is going to be something very similar to these two. Okay, it's going to be something between these two. Okay? So we define musical notes to be specific frequencies so that someone can produce the precise sounds to make a particular piece of music, right? But often, a number of musical notes are played together, okay? And we generally have certain sets of notes that sound pleasing together, called chords, okay? And in Western classical music, the most common chords are triads, which consist of 3 notes, okay? The number of half steps between notes dictates the chord. So, for example, a major chord would have 4 steps between the first and second note, and then 3 between the second and third note. Okay? So if I was going to play a C major chord, it would be C and then E and G, I believe. Is that right? Yeah, that's right. Okay. So a C major would be start with the one that's the name, and then go major says I go up 4 steps, that gives me my second note, and then I go up 3 more steps, and that gives me my final note. Okay? So C, E, G is our C major. And something like a C minor changes that to 3 steps up and then 4 steps up. Okay? So in a chord like this, in this, for example, this C major chord that I'm showing here, we're playing notes of different frequencies. And we just talked about beat frequencies, right? So since we have notes of different frequencies, we'll have beat frequencies here, right? And the beat frequencies in chords are high enough that they're the frequencies of other notes. Okay, so for example, in the C major chord where I have C, E, and G here, the difference between C4 and G4, so this would be the other way, right? So the beat frequency between G4 and C4 is equal to 130 hertz. Okay? But 130 hertz is a C3, a C that's 1 octave lower than this C. Okay? So when you play a C major chord, if you listen closely, you can kind of hear what we'll call like a phantom note. Okay? And that's a note that's lower than any of the 3 notes played. But you kind of get the impression, you kind of think that you can hear a C3 in this C major chord, right? This C4 major chord, even though it's not played. Okay? And that's coming from the beat frequency between the C and the G. Okay? So in particular, if you have a piano, and my wife plays the piano, so I showed this to her the other day, It's a very it's a very interesting effect. It's very spooky. So if you play just the C4 and the G4 together, okay, just the C and G together, and then you play the C3, right, and then you stop it and you play the C4 and the G4 again, you really do get the impression that you can hear that C3 being played at the same time as the C4 and G4. Okay, it's very interesting, and it's not played right. The frequency's not there, but the beat frequency, your brain is kind of interpreting that as another lower note. Okay. So that last effect, this chords having these kind of phantom notes in them, is the last kind of little interesting thing I wanted to point out about music, and it really just comes from this beat frequency. And beat frequency is something that's in every introductory physics class, every introductory physics book ever, but I've never heard them talk about these kind of phantom notes in chords before in an introductory class. Okay, so I just wanted to bring that up just as an interesting phenomenon that is our brain interpreting this physical phenomenon of beat frequency. Okay? And that concludes our lecture today. We learned a little bit more about music. We talked about standing waves in a column of air, right? And we talked about the beat frequencies, right? And I said we learned a little more about music. We didn't really learn anything about music. What we learned about was sound. We learned about sound through the lens of music, okay? We talked about musical instruments today, but really we're learning about sound and how sound waves work, okay? So we learned about standing waves in a column of air and beat frequencies, and we did it through the lens of music, okay? And this concludes the presentation of new material in this class, all right? What we're going to do with the remaining lectures is I'm going to use each one to review material that was covered in the class this semester, okay? And I'll conclude the semester with probably just one last lecture on untested material. This lecture is purely for your culture, as one of my professors used to say, okay? The last lecture that I want to do is one of the things that everybody always wants to hear about when they take a physics class or when you start telling them about physics is they always want to talk about relativity. Okay, relativity is the really kind of topic that people are excited about, right? They think about Einstein and how brilliant Einstein was, and then they think about relativity, and relativity is this really mind-blowing, mind-bending topic, okay? And so people always want to hear about that, always want to talk about that. So we don't have the tools to talk about relativity in this class. We don't have the mathematical tools or even the conceptual tools to really fully understand it. But what I'm going to do is for this last untested lecture period, I'm going to do relativity from just like the bird's eye kind of layman's point of view, just a very conceptual bird's eye view of relativity, just to talk about it because it's something that people usually find fun. Okay, so we'll make the last lecture in this class something that I think most people will be interested in and relieved that you won't be tested in it. Okay?